May 30th, 1942, 10:45 in the morning. The fleet carrier United States ship Yorktown cleared the channel at Pearl Harbor and turned her bow toward the open Pacific. To any observer on the shore, she looked like a combat-ready vessel, but her hull was a mosaic of industrial scar tissue. Just 72 hours earlier, she had entered dry dock number 1, with a jagged hole in her flight deck and her internal system shattered by a 500-pound bomb. Naval Intelligence and the Bureau of Ships estimated 3 months for a full refit. The strategic reality of the Pacific theater allowed for only 3 days. This was not a tragedy in the making, but a masterclass in aggressive engineering and the cold logic of naval salvage. 1,400 workers descended on the hull like a mechanical swarm. They did not aim for aesthetic restoration, they aimed for immediate structural viability. Over 300 miles of welding rod were consumed in a frantic effort to seal the breaches and reinforce the longitudinal girders. This was not craftsmanship, it was industrial triage performed at a scale that defied standard maritime practice. The welders were still cutting away temporary brackets and sealing final seams as the dry dock flooded and the ship began to move under her own power. The goal was to transform a sinking wreck back into a weapon through the sheer volume of steel and thermal energy. Every inch of that welding rod represented a decision to prioritize function over form under the ticking clock of an impending fleet engagement. The engine room functioned as a chamber of controlled violence. During the previous engagement at the Battle of the Coral Sea, the impact of a bomb had threatened to turn the boiler uptakes into a massive internal incinerator. The Black Gang, the engineers who operated deep below the waterline, understood the physics of catastrophe better than anyone. They utilized a specific mechanical technique known as smothering. When a strike threatens the integrity of the fire rooms, the risk is not just the fire itself, but a fuel-air explosion within the exhaust system. By flooding the uptakes with carbon dioxide, the engineers effectively replaced the oxygen necessary for combustion. This smothered the tactical threat of an internal blast and prevented the heat from deforming the primary bulkheads. It was a calculated gamble involving gas density and pressure. This mechanical logic allowed the Yorktown to survive long enough to reach the repair yard and eventually the waters northwest of Midway Atoll. The ship displaced 25,500 tons at full load, and every pound of that weight was now a variable in a high-stakes engineering equation. The ninth boiler, which had been snuffed out by the shock of aerial bombardment, was forced back into service through manual overrides and raw persistence. The engineers understood that a carrier without speed is merely a massive target on the surface of the sea. They pushed the 9 Babcock and Wilcox boilers until the 4 screws were turning at a rate sufficient to achieve 20 knots. It was an efficiency born of industrial desperation and calculated risk. The hull was essentially a pressurized vessel, held together by fresh welds and the determination of a crew that had refused to accept the 3-month estimate provided by the bureaucrats. The carrier that should not have been there was now steaming toward a rendezvous with naval history. She carried her full complement of aircraft and a crew that had lived through the thermal stress of a near sinking. The structural load paths of the ship had been altered by the repairs, and the internal geometry was no longer as it was designed at the shipyard in Newport News. But the mission did not require perfection, it required presence. The question remained whether a ship held together by 300 miles of fresh welds could withstand the hydrostatic pressure and kinetic energy of modern naval warfare. The first tests of that structural integrity were only hours away, and the ocean does not negotiate with human deadlines or engineering miracles. The strategic weight of the Pacific War now rested on a hull that by all laws of naval architecture should have still been sitting in a dry dock in Hawaii. 26 degrees. That is the angle where a Yorktown-class carrier reaches its point of no return. At that inclination, the flight deck becomes a useless slab of steel, and the internal bulkheads begin to experience stresses they were never designed to manage. On June 4, 1942, at 14:45 in the afternoon, the Yorktown was pushed to this mathematical limit. 2 Type 91 torpedoes launched from Japanese aircraft slammed into the port side. The impact was not merely an explosion, it was a massive injection of kinetic energy that shattered the transverse bulkheads and opened 3 boiler rooms to the sea. The ship did not just list, it began a slow, agonizing roll that threatened to invert the hull and eventually send it down to 16,000 feet of water. To understand why the ship survived this initial trauma, one must understand the relationship between the center of buoyancy and the center of gravity. A ship stays upright because these two forces remain in a state of dynamic equilibrium. When water floods the portside fire rooms, it creates a massive weight shift that pulls the center of gravity away from the vertical centerline. This creates a heeling arm that tries to pull the ship over. The counter move is a process called counter-flooding. By intentionally opening valves on the opposite side of the ship, the engineering team can add weight to the starboard compartments. This moves the center of gravity back toward the middle and restores the upright posture of the vessel. It is a terrifying logic that involves inviting more water into a dying ship to keep it from capsizing. While the deck crew prepared for abandonment, the men in the engine rooms were engaged in a different kind of combat. Thick black smoke from the bombed uptakes filled the lower decks, making breathing nearly impossible without respirators. Despite the 26-degree list and the imminent threat of total flooding, the engineers refused to vacate their stations. They utilized the smothering technique to keep the fires from spreading to the fuel tanks while simultaneously working to relight the remaining boilers. Through a series of manual overrides, they managed to restore steam pressure to the turbines. Within 2 hours, a ship that the Japanese aviators had reported as dead in the water was making 20 knots. This speed was critical for providing the maneuverability required to dodge the next wave of attacks and demonstrated that the ship still possessed a functioning mechanical heart. Despite the restoration of power, the physical damage was accelerating. The structural integrity of the hull had been compromised by the combination of bomb blasts and torpedo impacts. Progressive flooding began to find its way through distorted pipe runs and buckled hatches. At 1500 hours, Captain Elliot Buckmaster looked at the 26-degree list and realized the ship was no longer a stable platform for combat operations. The risk was that the ship would suddenly lose all stability and roll over before the thousands of men on board could escape. He gave the order to abandon ship. But as the last sailors slid down lines into the Pacific, the Yorktown did something unexpected. She stopped rolling. The counter-flooding and the inherent buoyancy of her remaining intact compartments reached a temporary stalemate with the ocean. The carrier wallowed in the swells like a wounded giant. Her boilers were silent and her flight deck was empty, but the geometry of her hull was still fighting for survival. The center of buoyancy had shifted enough to provide a small margin of safety. This was the moment where the salvage operation transitioned from a desperate combat repair into a surgical engineering problem. The ship was a derelict, but she was not yet a wreck. She sat in the water for another 18 hours, proving that the initial 72-hour repairs at Pearl Harbor had provided a foundation of strength that exceeded all expectations. The Yorktown was refusing to die because her internal skeleton was still resisting the massive hydrostatic loads of the deep. But this reprieve was temporary. The engineering stalemate was about to be broken by a different kind of threat. One that would strike from below and finish what the bombers and torpedo planes had started. A ship without a crew is legally a derelict, but mechanically it remains a complex system of stored energy and failing boundaries. On the morning of June 6, 1942, the Yorktown presented a logical paradox to the United States Navy. She had been abandoned for nearly 20 hours, yet she refused to capsize. This suggested that the initial damage had reached a state of temporary equilibrium. To capitalize on this stability, a skeleton crew of 170 men was ordered back onto the listing deck. Their mission was not to fight a battle, but to execute a high-stakes industrial salvage operation in the middle of a combat zone. They were attempting to reverse the laws of physics that were pulling 25,000 tons of steel toward the seafloor. The primary tool for this resurrection was the destroyer United States ship Hammond. The smaller vessel was moored directly to the starboard side of the carrier, acting as a mechanical life support system. Through a series of thick cables and hoses, the Hammond provided the electrical power and high-pressure pumping capacity that the Yorktown could no longer generate for herself. This was an umbilical cord of energy. The engineers used this external power to activate the remaining submersible pumps and begin the process of clearing flooded compartments. This was the strategic application of counter-flooding in reverse. By removing the water they had intentionally admitted the day before, they hoped to shift the center of gravity back to a position that would allow the ship to be towed to Pearl Harbor for permanent repairs. While the pumps worked, the salvage crew began the brutal physical labor of lightening the ship. In naval engineering, every pound of weight located above the waterline acts as a lever that increases the risk of capsizing when a ship is listing. To combat this, the crew began jettisoning everything that was not essential to the survival of the hull. They used cutting torches to remove the massive 5-inch anti-aircraft guns and pushed them into the sea. They cleared away shattered aircraft and heavy equipment. This was a direct manipulation of the ship's stability curve. By stripping weight from the high side and the upper decks, they were reducing the rolling moment and allowing the hull to right itself. This process of lightening the ship involves the complex management of structural load and torsion. A carrier hull is essentially a massive steel beam that must support its own weight while being buffeted by ocean swells. When a ship is damaged, enlisting the load paths through the longitudinal girders and transverse frames are distorted. This creates torsion where the hull tries to twist along its axis. By strategically removing weight, the salvage team was attempting to relieve these internal stresses and prevent a catastrophic structural failure. If the torsion became too great, the steel would reach its elastic limit, and the hull would literally snap under the weight of its own flooded compartments. The 170 men were working inside a giant machine that was under extreme tension, where a single failing weld could lead to total collapse. The engineering effort was succeeding. By early afternoon, the list had been reduced from 26 degrees to 22 degrees. The ship was being taken under tow by the tug Navajo, and it appeared that the Yorktown might actually survive her second brush with death in a single week. The crew had managed to stabilize the internal flooding, and the umbilical cord to the Haman was providing the necessary energy to keep the remaining systems alive. But salvage operations are inherently vulnerable to external variables that cannot be controlled by a welding torch or a pump. At 13:35 in the afternoon, a lookout spotted a thin line of white water 5 miles away. A Japanese submarine, the I-168, had spent 18 hours stalking the crippled carrier. The salvage crew was about to learn that the most dangerous pressure on a hull does not always come from the depth of the ocean. The final test of the Yorktown's structural integrity was moving through the water at 40 knots. 13:36 in the afternoon. That was the precise moment the engineering stalemate was broken by 4 tons of high explosives moving through the water. Commander Yahachi Tanabe, aboard the submarine I-168, had closed the distance to 1,400 yards before releasing a spread of 4 torpedoes. The tactical objective was the carrier, but the physics of the engagement would claim 2 victims. 1 torpedo missed the mark entirely. The second struck the destroyer Haman, which was still moored to the carrier, acting as its mechanical life support. The force of the detonation was sufficient to snap the steel keel of the destroyer instantly. As the Haman began to founder, the 3rd and 4th torpedoes passed directly beneath her and slammed into the starboard side of the Yorktown. The impacts occurred at frames 95 and 120, creating breaches 15 feet in diameter. In a healthy ship, these holes might have been manageable through counter-flooding and damage control. But the Yorktown was no longer a healthy ship. She was a compromised structure held together by the 72-hour welds from Pearl Harbor and the sheer grit of a skeleton crew. The Haman vanished beneath the surface in less than 4 minutes, taking 80 men with her. However, the most significant damage to the carrier was not caused by the torpedoes themselves, but by the sinking of the destroyer. As the Haman descended, her depth charges remained set to active. When the ship reached the pressure threshold for detonation, the charges exploded directly alongside the Yorktown hull. This event triggered a mechanical crisis known as hydrostatic shock. Because water is nearly incompressible, it acts as a highly efficient conductor for explosive energy. Unlike an explosion in the air, which expands in all directions, a deep water blast sends a concentrated shockwave through the water column. This shockwave hit the Yorktown with the force of a massive hydraulic hammer. It did not just bend the steel plating, it shattered internal cast iron pipes and forced thousands of rivets to shear off simultaneously. This shockwave essentially vibrated the entire 25,000-ton hull with enough frequency to open every existing seam that had been stressed during the previous 3 days of combat. This was the catalyst for progressive flooding. Progressive flooding is the slow, unstoppable migration of water through a ship. It occurs when primary bulkheads are compromised and secondary barriers like hatches and ventilation ducts fail under the increased pressure. The hydrostatic shock from the depth charges had turned the Yorktown into a sieve. Water was no longer just entering through the 15-foot holes on the starboard side, it was seeping through every rivet hole and hairline fracture across the entire lower hull. The skeleton crew of 170 men was forced to realize that the umbilical cord to survival had been severed. The pumps were gone with the Hammond, and the internal list was no longer responding to manual intervention. The final paradox of the Yorktown began to emerge as the sun set on June 6th. Despite the two massive torpedo strikes on the starboard side, the ship did not roll toward the damage. The internal geometry was shifting in ways that contradicted standard salvage expectations. To understand this, one must revisit the center of buoyancy. The cumulative damage from the port side aerial torpedoes 2 days prior had already weakened the internal supports on that side. As the new flooding from the starboard strikes and the depth-charge shockwave filled the lower compartments, the center of gravity did not move in a straight line. Instead, the ship began to settle deeper and slowly lean back toward the port side. By 5 in the morning on June 7th, the list had reached 27 degrees. The ocean was finally winning the war of attrition against the 300 miles of welding rod. The carrier was about to begin a 3-mile descent to a volcanic plain where the light of the sun never reaches. The weight of the water column at 16,650 feet is a mathematical impossibility for almost any structure not designed specifically as a pressure vessel. At this extreme depth, the ambient pressure reaches 7,200 pounds per square inch. This is the equivalent of a heavy tank resting on every square inch of the hull. When the Yorktown slipped beneath the surface at 6 in the morning on June 7, 1942, she began a 3-mile vertical journey into the abyss. This was not a simple sinking, but a complex exercise in differential pressure. As the ship descended, the air trapped inside the various compartments was subjected to the massive compressive force of the Pacific. If the internal pressure does not equalize with the external pressure, the steel will succumb to catastrophic implosion. In 1998, a joint expedition between the United States Navy and the National Geographic Society arrived in the waters northwest of Midway to find what the ocean had hidden for 56 years. They utilized a specialized deep-towed side-scan sonar system. To understand this technology, one must visualize sound as a flashlight in an otherwise pitch-black room. Side-scan sonar sends out acoustic pulses that bounce off the seafloor and return to a receiver. When these pulses hit a large object like a carrier, they create side-scan sonar shadows. These are not true shadows caused by light, but are acoustic voids where the signal is blocked by the mass of the wreck. By analyzing the length and shape of these acoustic shadows, the search team could reconstruct the three-dimensional geometry of the ship before a single camera ever caught sight of the hull. The search culminated in the deployment of the remotely operated vehicle known as Curve 3. This was a sophisticated underwater robot equipped with high-intensity lighting and cameras designed to survive the hostile environment of the deep. As the vehicle reached 16,650 feet, it encountered a landscape of volcanic silt and eternal darkness. The cameras began to transmit images of a ship that looked remarkably intact. This was a direct result of the progressive flooding that had occurred during the final hours of the salvage attempt. Because the ship had filled with water before it sank, the internal and external pressures remained in a state of dynamic equilibrium during the descent. This meant the hull did not implode, but instead settled gently onto the seafloor. The first definitive proof of the identity of the vessel came when the cameras focused on the bow. Despite 5 decades of exposure to the corrosive chemistry of the deep ocean, the hull number 5 was still clearly visible through the thin layer of silt. This is a fringe detail that speaks to the high quality of the paint and steel used in 1930s naval construction. The island superstructure was still standing, and the bridge windows remained clear as if the ship were still on active patrol. The wreck was sitting perfectly upright on the volcanic plain, suggesting that the internal weight distribution and the center of buoyancy had stabilized during the long fall to the bottom. The Yorktown was no longer a dying ship, but a silent monument to the engineering that had kept her afloat through 3 days of sustained combat. However, the visual survey revealed an anomaly that the search team did not expect. While the hull and island were largely preserved, the stern of the ship showed signs of a violent structural separation. The massive flight deck overhang, which should have extended over the screws, was missing. This missing piece of anatomy suggested that the forces of the descent were not entirely benign. The cameras revealed that the steel had been torn away with a ferocity that contradicted the otherwise peaceful state of the wreck. This discovery forced historians to reevaluate the final moments of the descent and the mechanical stresses involved. When 25,000 tons of steel encounters the differential pressure of the deep, the search had answered where the Yorktown was, but it had opened a new question about what happened during her final 3-mile plunge. The wreck of the United States ship Yorktown presents a logical paradox that challenges the reliability of human observation under extreme mechanical stress. For 56 years, official naval records and survivor accounts maintain that the carrier rolled to her starboard side as she succumbed to the sea on the morning of June 7, 1942. The physical evidence discovered 3 miles down in 1998 tells a different story. The wreck sits upright on the seafloor, but the forensic distortion of the hull proves that the ship actually rolled to port. This discrepancy is not a result of dishonesty, but of the psychological and physical environment of a dying ship. When 25,500 tons of steel begin to fail, the sensory input for the crew becomes a chaotic blur of noise and motion. The cameras of the remotely operated vehicle have corrected the historical record by providing a cold, objective witness to the final movements of the hull. The visual survey conducted at 16,650 feet revealed that the 3-mile descent was a period of intense structural reassessment for the ship. As the Yorktown plummeted, the internal load paths that were already compromised by 3 days of combat finally reached their elastic limit. This resulted in the missing flight deck overhang at the stern, which was likely sheared off by the torsion and drag forces acting on the vessel as it fell through the water column. This specific mechanical failure highlights the violence of the vertical journey. While the main hull remained largely intact due to the equalization provided by progressive flooding, the external structures were subjected to the unpredictable physics of a high-speed descent. The absence of the ship bell is another detail that remains an open question for maritime historians. It may have been torn away during the initial roll or lost to the hydrostatic shock of the sinking, but it remains missing from its mounting. The wreck has now transitioned from a combat vessel into a unique biological and chemical laboratory. Marine scientists used the site to study the corrosion rates of steel from the 1930s under the specific chemistry of the deep Pacific. The hull supports a thriving ecosystem of amphipods and grenadier fish that navigate the silent corridors of the island superstructure. This is the irony of naval salvage. A machine built for destruction and then destroyed by it now serves as a foundation for life in a region where nutrients are scarce. The acoustic shadows once seen on the sonar monitors have been replaced by high-definition images of a ship that seems to be standing watch over the volcanic plain. Strategic analysis of the Battle of Midway suggests that the presence of the Yorktown was the critical variable that secured a victory for the United States. Her dive bombers delivered 1/3 of the killing blows against the Japanese carrier force, and her resilience bought the American fleet the time needed to launch final strikes. Without the 72-hour miracle repairs at Pearl Harbor, the strategic depth of the Pacific theater would have been fundamentally shallow. The carrier was not just a participant in the battle, she was the pivot point of the entire engagement. Her refusal to die until the strategic objective was met is an example of heroism expressed through structural durability and engineering ingenuity. The Yorktown is now protected under the Sunken Military Craft Act, which designates the wreck as a permanent war grave. She belongs to the 141 men who went down with her and the 80 souls from the destroyer Haman, who rest in the debris field nearby. This site is a place of remembrance where the coordinates represent more than just a location on a chart. They represent the final resting place of a ship that altered the trajectory of a world war. The ocean preserves her secrets in a state of eternal darkness where the temperature remains near freezing and the pressure is constant. 3 miles down, the carrier remains a silent witness to the logic of sacrifice and the ultimate limits of naval engineering.